Okay, hi guys. So in this video lecture, we'll be starting off with the ring chain isomerism, and in the later part, we'll be seeing tautomerism as well. Okay, so let's start with ring chain. Okay, so what is ring chain? So ring chain is simply if one isomer is open chain and another isomer is cyclic, then it is called ring chain. Simple. Okay. If one isomer is open chain and another is cyclic, then it is called ring chain isomerism. Okay, let us look at the examples. We have, so what would be the ring chain of this? This is the chain form. What would be the ring form of this? Simple, cyclopropane ring. If you count the number of hydrogen atoms here, they are 6 here. If you count the number of hydrogen atoms here, they are also 6 here. Okay, remember that the dB should not change. I mentioned in the dB video tutorials that the dB of a pi bond and dB of a ring are both to be considered as 1. Okay, so this is based on dB concept only that we are having ring chain isomerism in the picture. Okay, this is another example. Okay, so let's talk about, I think this was the 5th. Let's talk about 6th type of isomerism, which is called tautomerism. Okay, so what is tautomerism? Tautomerism is simply, it's also called slow isomerism, and I will tell you the reason why it's called slow isomerism. If two functional isomers are in dynamic equation with each other, then they are tautomers. So just write it like, if two functional isomers are in dynamic equation with each other, then they are known as tautomerism. Okay, so let's take some example to understand what is tautomerism. We have a nitrile and we have this compound, so they both are in tautomerism. So if I have this keto form, I can actually remove this alpha hydrogen and the pi bond can go to here and the negative charge will go back to the oxygen atom, and then the removed H plus ion will actually be collected by O minus. So we will have something like this. Okay, third is we have like this. So we remove this alpha hydrogen, negative charge goes here, and the H plus form will be collected by O minus. So or rather, it's not a benzene, let's only be simple cyclohexane, because in benzene structure it was not possible. So double bond will come here, OH will come here. Okay, so one thing to notice in this form is, and one more thing, how did this actually happen? This also we can show it as negative charge come here, hydrogen atom would be collected by nitrogen. Okay, so this would be formed. Okay, so this can also be written as, means tautomerism can be seen in only those compound in which we can see the alpha hydrogen to be removed and there would be a conjugation in between the pi bond and the more electronegative element, or simply put, alpha hydrogen should be removable. should be removable. Okay, so let's talk about some more examples of um, hmm, some more examples wherein you need to identify which type of isomer it is. So we have, suppose I have this and I have this. So which two isomerism are the two compounds following? Obviously they are ring chain and they are functional. Why? This was a aldehyde group and this was a ether group. Okay, let's take some another example. We have, okay, so I'm just writing this for reference. RTFMCP. Here you can wherein I have written the name of all structural isomers, isomerism. R is for ring chain, T is for tautomerism, F is for functional group, functional isomerism, M is for metamers, C is for chain, and P is for position isomer. Okay. Now let us see for this compound. We have a keto group here and we have a keto group here. It is a ring chain? No. Is it a tautomer? No. No alpha hydrogen removal and no conjugation and resonance is seen here. Is it a functional? No. In both the compound, the keto group, only the keto group is present. Is it metamer? Yes. Why? Because the alkyl group on either side of keto group is changing, so it is a metamer. Is it a chain? No, it's not a chain. Is it a position? Yes, the position of the functional group is changing. Okay, let's look at this example. Is it a ring chain? No. Is it a tautomer? If it had been a tautomer, then OH would come here and here should come the pi bond, not here. It's not a tautomer. Is it a functional group? Is it a functional isomer? Yes. Is it a metamer? No. Why? Because functional group is not same. Is it a chain? No. Is it a position? No. Okay, so let's draw structural. Let's come to the second set of examples wherein you have to draw structure isomers of the following. Draw structure isomers. Okay, let's start with first compound. You are been given with C5H12. So let's start with RTFMCP. Can we draw a ring chain? So if we calculate the dB of this compound, it comes out to be C plus 1 minus H plus X minus N by 2. dB is 0. So if dB is 0, ring cannot be formed. Can it be tautomer? Tautomer only exists when there is a double bond. dB is 0, no tautomerism. Okay, let's talk about functional group. Can there be attached any functional group? No. Can there be any metamer? If there is no functional group, there cannot be a metamer. We cannot talk about position. We can only draw the chain isomers of this compound. So let's draw the chain isomers. First is this, second, third, let's draw some more. If I draw the C here, it would be 4 chain. If I draw C here, it would be, if I draw C here, it would again be 4 chain. So I can actually draw this. Anything else I can draw? No. So number of isomers in this case is 3. Let's talk about this C6H14. So what is the dB of this compound? If we calculate the dB is 6 plus 1 minus H plus X minus N by 2. So I hope you remember the dB formula. dB formula is C plus 1 minus H plus X minus N by 2. Okay, if you have forgotten what is DBE, go back to the lectures in which I have talked in very expanded form, and we have done so many examples of calculation of DBE. I think by this time you should be very much fluent with this formula. So the DBE for this is 0, hence there cannot be ring chain, no tautomerism, no functional group, no metamer if not functional group is there, no position, there is no functional group. So only possibility is it can be having chain isomers. So 1 2 3 4 5 6, 3 4 5 6 can be here, 1 2 3 4 5 6 can be here. If we draw the same, this would be and this would be same, hence I am not drawing this, we are not calculating this. Let's calculate for 4 when the principal carbon chain is of 4 atom. If I put the fifth carbon atom cannot be on this and this, fifth carbon atom can be here, so it is a length 4. For length 4 I can also draw something like this, it's also length 4. Okay, let's draw something of length 3. If something of length 3, substituent cannot become on this carbon atom, because if the substituent comes on this carbon atom, the length would be 4. Okay, length 3. So if I draw anything here or anything here, again the length would be 4, so this is not possible. Okay, so how many did we came across? Okay, one more thing can be, are we missing anything? No, I don't think we are missing anything. The answer should be 5, and it is 5. Okay, so let's calculate about this. So dB, if you calculate the dB of this compound, it will come to be 0 again. So only chain isomer is possible in this case. Let's draw the chain isomers of this following, so 1 2 3 4 5 6 7, 1 2 3 4 5, these are 6 only, so 7 3 4 5 6. I'll substitute one remaining carbon atom, and then also can put the carbon atom here. But when I draw the some other structure, and when the carbon atom, okay, so if I count the substituent methyl group which is attached to this carbon atom, I can see that it is attached as third carbon atom, and here also it is attached at third carbon atom. So this and these are same, hence I am not drawing this. If I attach it here also, I have already the structure present. Okay, so no more with 6 number of carbons as principal chain. Let's start with 5. Okay, so 5 here we have to add 2 remaining. So 2 remaining cannot be here and here. 2 remaining can be here, either here, or 2 remaining can be here. And if I again draw the 2 same remaining on this carbon, it would be same as this carbon, so not redrawing that again. So 5 and 2 remaining can be drawn on here and here, and if I draw the last, which is on both these 2 carbons, we can actually rotate that, and that would be matching with this compound only, so I'm not redrawing it. So let's have with 4 as a principal carbon chain. So this is the principal carbon chain, we cannot have one here on here, we have 3 more to add. So if we add one here, this carbon's valency is completed, cannot add anything more here, and one here. Okay, so I think it's pretty much completed, because now let's say whether we can draw with 3 carbon atoms, or remaining carbon atoms to be substituted are 4, 1 2 3 4. So parent carbon chain actually increases to 4, it's not remaining 3. so we cannot draw something like this. So how many total isomers? 1 2 3 4 5 6 7, I think 8, or am I missing anything? 1 2 3 4 5 6 7 8. So uh, let's make it again. This is the one. Let's see if we are not missing anything. This is the second one. This is the third one. Now this is the fourth one. This is the fifth one. We can actually also draw something like 4. No, this is done. Okay, so this is the sixth one. So this is the seventh one. And this is the final eighth one. Okay, so I think 8 would be the answer for this case. Okay, so let's draw for C4H9Cl. So dBE for this compound would be C 4 plus 1 minus 9 plus 1 minus 0 by 2. So dB again would be 0. So let's draw for this 1 2 3 4. Cl can be here, here. This is the four carbon principal chain. Okay, so only chain isomers are possible for this case. Let's talk about when there are 3. So it can be either here or it can be either here. So 4 isomers are possible. Let's talk about this case, C3H8O. Let's calculate the dB. dB is 3 plus 1 minus 8 by 2, which is 0. So only chain are possible for this case also. So let's draw all the possible chain isomers. Chain is, it can be OH here, OH here. Let's talk about ether group. So for ether group also only one. Let's talk about chain with only 2 carbon possible. So I think they are already covered in the ether group. Okay, so total number of isomers for this would be 3. Why? One is primary alcohol, secondary alcohol, and one is ether. No more possibilities are there. Okay, so chain and position both are possible. Okay, functional group is changing. Okay, so with this lecture we come to an end of seeing the examples. So in the next lecture we'll be covering up more examples on the same, so you will have a better clarity on figuring out total number of isomers for a given compound. So till then, good luck and goodbye.